I'm going to show you some examples on how to do the definite integration to find the area. When we use definite integration to find the area, there are three major items we want to think about. Number one is whether we want to split it up in the vertical slicing or whether we want to do it with the horizontal slicing. With vertical slicing, that would be dx, alright, and the length of each this rectangle will be y, so that is integrate y dx. On the other hand, if we do the horizontal slicing, the length of each this rectangle is x, and the width is dy, alright, so that is x dy. So we have to choose whether we do the vertical or horizontal. Now secondly, that is the boundary. If we do the vertical, then it should be the boundary for x, alright, x from A to B, alright. On the other hand, if we do the horizontal, then it should be the boundary for y. Y should be from P to Q, alright. So even the same area, the way that you slice it up will change the boundary. Number three is whether do we need to split into two different portions, 1, 2, or sometimes maybe the third one, alright, because each one requires a different formula for the definite integration. So first, let me show you one example that we can use both vertical and horizontal slicing to do the problem, right? So we want to find the area between the red and the blue. The blue curve is the one like this. The blue one says y is x minus 1 squared. That is the blue one. Right, x minus 1 complete square. That is the blue one. And then we have the red one. The red one goes something like this. And it is y is x minus 1 square root. Alright. Now the first thing you need to do is to find the intersection points. Intersection points. It controls the boundary. This intersection point is 1, 0. We can solve between the red and the blue to get this. This red point is 2 and 1. Alright. Now we'll come back to this later on as the boundaries. So in the first approach, we do it with a vertical slicing. Alright. So we split it up like this. When we do it like this, we have the red. Now for each of this part, we have the red over the blue. So we have the red y subtract the blue y. Alright, and then we integrate with dx and then the boundary. It should be the boundary for x. Alright. At this point, x is 1. To there, x is 2. So the boundary should be from 1 to 2. This is how we construct the area from vertical slicing. And the result goes to something like this. Square root of x minus 1 subtract x minus 1 squared dx. Alright. And that is 2/3 x minus 1 to the power of 3 over 2. Subtract from it 1/3 x minus 1 cube. Right. Integrate from 1 to 2. Now I'm not going into the details. If you put 2 and 1 into this expression, you got the answer equals to 1/3. I leave it to you as an exercise. Alright. So that's how we do the vertical slicing. At the same time, the same question can be dealt with horizontal slicing. We split it up horizontally, alright? But when we do that horizontally, now there are two things we need to know. First, we have the blue x is on the right hand side of the red x. So each of this rectangle, the length is the blue x subtract the red x, alright? And then we integrate, we multiply to the width of each of this, that is dy, alright? Dy, sorry. And the boundary will be from smallest y, this is y equals to 0, all the way up here, y equals to 1. So the boundary is from 0 to 1, that is the area. Now we need to convert x as the subject, that means, alright, so we have x is the square root of y plus 1 for the blue. For the red, we have x is y squared plus 1. Alright, so we put all of this into the integration with from 0 to 1. The blue x is square root y plus 1. The red x is y squared plus 1. Alright, the 2 plus 1, I think they got cancelled. Alright, dy. So this goes to 2/3 y 3 over 2 and subtract 1/3 y cubed. The integration from 1 to 0. And once again, if you put back the 1 and 0 into this bracket, it goes to the same 1/3. Alright. So this example contrasts how to deal with the integration with vertical and horizontal slicing. Alright, sometimes questions like this, they can do it with either way. You can do it vertically or horizontally. But then notice that if you do it vertically, then it should be y dx. If you do it horizontally, it should be x dy. And which subject what is important, and also the boundary. Okay, so this is example number 1. And then there is an example number 2 on a region like this. Alright, you have the red curve. The red curve goes y is sine 2x. Alright, and then we have the blue curve. It goes y is the blue curve is like this. Alright, it goes y is cosine x. Alright, so we need to find the area. Now for this, the area between the red and the blue. So I think it is best done with vertical slicing. I believe it's very difficult to do it with horizontal slicing. But there are 2 regions in this problem. The one is the first region right here. Let's call it A. Alright. In the region A, that is the blue is over the red. So we have the blue subtract the red. But then in region B here, we have the red above the blue. So it's the red subtract the blue. So we have to split it into 2 parts. And also we need to find the boundaries. What are these values of x? Alright. What are these values of x, so that we can have the proper boundaries. We can do it by solve the equation. Sine 2x equals to cosine x. Alright, we can solve this equation. And sine 2x is cosine x. Alright, so sine 2x is just twice sine x cosine x equals to cosine x. So we have cosine x is 0 or sine x is 1 over 2. Alright, that is x is pi over 2, or x is pi over 6. Alright, so this is 0, this is pi over 6, this is pi over 2. Now these numbers are useful for the boundaries. So let's do A and B separately. We have part A. Alright, part A will be from 0 to pi over 6. Alright, the red y minus the blue y minus the red y, because the blue is above the red. Alright, so this integration. Now it helps to know what is the integration of sine 2x. Alright, the integration of sine 2x will be 1 over 2 cosine 2x. Alright, once again I leave it as an exercise for the indefinite integral. You can easily do it with an integration by substitution. Alright, so anyways, this will be sine x plus, that is a minus here, plus 1 over 2 cosine 2x. Alright, from 0 to pi over 6. And that goes to 1/4 if you put back the pi over 6 and 0 into the equation. By similar token, for part B, notice the boundary is different. It's from pi over 6 to pi over 2. In this range, it should be the red subtract the blue. Alright, so it is sine 2x and then subtract cosine x. Alright, it should be the red subtract the blue. That's why we need to split into A and B, because they follow different equation in each region. Alright, and pay attention to the boundary. Okay, so in B we have this. We have, it's almost the same. We have minus sine x minus 1 over 2 cosine 2x. Alright, and this from pi over 2 to pi over 6. If you want to put back the pi over 2 and pi over 6 into this, you have the answer is also the same 1/4. So the total area is the sum of these two. The area will be just A plus B, and that goes to 1 over 2. That is the answer to this particular area. Okay, so there are some other exercises in part 2. There are some other examples in part 2 and part 3 to follow. Thank you.